Algebra 2, Chapter 17, Section 3, Probability. The probability of an outcome is a measure of how likely that outcome is. When we say outcome, we mean the outcome of an event. Okay, it's kind of generic, but you'll see this can be lots of different kinds of events. So some context, a probability of 1 means the outcome is certain. So if we say we flip a coin, it will land on heads or tails. The probability of that is 1. That's going to happen. Either heads or tails will happen. The probability of 0 means the outcome is impossible. What would be the probability of flipping both heads and tails at the same time? That's not possible. It would be 0. Okay, so 1 means the outcome is certain, 0 is impossible. We often express probability as percent. You might hear people say, I'm 100% confident, which means they're certain. Or we might even have 0%, which would mean impossible. Probability is defined as the ratio of the number of ways an outcome can occur. So probability is the number of ways an outcome can occur, or an event occurs, to the total divided by the total possible outcomes. Okay, we could say then the probability of flipping a coin and it landing on heads. There's one way for it to land on heads. There's two possible outcomes. It's 1/2, which would be, as a percent, 50%. So let's do a simple example. Shannon buys 10 tickets in a lottery with 500 entries. What is the probability of her winning? So the probability of her winning, I think this is spelled wrong. Winning, no, maybe that is right, winning. Probability of winning would be the number of ways she can win. So she has 10 possible ways of winning because she has 10 tickets, over 500 tickets. Okay. Presumably only one of those 500 wins. Otherwise, this analysis wouldn't be correct. So there's just 10 possible chances of having the winning ticket of the 500 tickets. And that would be 1 over 50, which is, as a percent, 2%. There are 535 members of the Congress of the United States, 100 in the Senate, and 435 in the House. In 2020, the state of California has 53 representatives in the House. What is the probability that 1, a randomly picked member of the House, represents California? So there's 53 Californian members of the House out of the 435 people in the House, which would be (53) over 435, 12.18% or so. So this is a rounded number. This ratio is the exact probability. So either of these is okay as an answer. 2, a randomly picked senator represents California. Well, there's 2 Californian senators of the 100 senators, which would be 2%. 3, a randomly picked member of Congress represents California. So there's 53 members of the House and 2 of the Senate of the possible 535 that we could pick. So that'd be 55 over 535, or 10.28%. And notice we couldn't have just added or subtracted the answers from 1 or 2 to get 3. We have to actually go back to the definition and think about the number of ways it could happen over the total, because the total, the denominator is different for all 3 of these. For a randomly picked member of Congress, sorry, there's a typo here, member of Congress does not represent California. Well, if they don't represent California, it would be one of the other people. So that would be the total 535 minus the 55 from California. So we would have 535 minus 55, 480 over 535, 89.72%. And you might say, oh, those add up to 100%. And they do, and that will always be true. So the probability, and we'll talk about this notation in a minute, but the probability of A plus the probability of, we'll use a logical operator, not A. Okay, so this tilde means a not. So if the probability that A happens plus the probability that A doesn't happen will always be 1, because one of the two things must happen. Okay. So we, as I just pointed out, we can write the probability of an event as P of E, kind of like function notation, but it's not exactly a function. So for instance, if we roll a 6-sided die, if E1 is the event of rolling a 1, the probability of E1 would be 1/6, because there's 6 sides, only one of them has a 1 on it. Okay, so that was basic probability. Now let's talk about some more complicated probability. Joint probability is the probability of two events occurring together, and is written as probability of A intersect B. So you read this upside down U-ish kind of shape as intersect. And this comes from set notation, set theory, which we've not talked thoroughly about in this class. But that's where this notation comes from. And it means essentially, in this kind of context, logical and. Okay, so B, A, the probability of A and B. So you could also read this as and. Although the symbol we normally use for and is this triangle kind of symbol, not this cap symbol. So if we're flipping a coin twice, event A is landing ahead on the first flip and B on the second flip. The probability of, the joint probability of A and B, or the probability of A and B, which we'll just read this as and for our probability class and forget about this intersect, but that's where that came from. So the probability of A and B is 1/4, and that comes from the fact that when we flipped a coin twice, there's two sets of events, so there's 4 possibilities, and for us to get ahead on both, we have to have just one of those 4 possibilities, so that gives us a probability of 1/4. So that was joint probability. And a related concept is conditional probability. Conditional probability is the probability of event A given that event B occurs, and is written as the probability of A, and we read it this bar as given B. Okay? So the probability of A given B. For a deck of cards, event A1 is drawing an ace from a freshly shuffled deck, and event A2 is drawing an ace for the second card. So the probability we draw an ace on the first card, well, there's 52 cards we could draw from, and 4 of them have an ace. So it would be 4 52nds, which is 1/13, which is about, use a calculator, it's about 7.7% chance you draw an ace, because there's 4 of them. Now, what's the probability the second card we draw is an ace given the first card that we drew was an ace? So that's what we have, A2 given A1. So A2 is the second card being an ace, A1 is the first card being an ace. So this is saying I drew an ace after drawing an ace. What's the probability of that occurring? Well, since in the first event we drew one of the 4 aces, the deck contains 51 cards, and only 3 of those cards are aces. So our probability of drawing an ace the second time, given we drew an ace the first time, is 3/51, or about 5.8%. So you can see that because there's less aces to draw, our probability has gone down. We can also find the conditional probability from the joint probability. So if we can find the joint probability, then we can divide that by the probability of the thing that's given, and that'll give us the conditional probability. So if we know the probability of A and B happening, and we can divide that by the probability of just B happening, and that'll tell us what the probability of A is given that B has happened. And this works either way. Because and, it doesn't matter. B and A is exactly the same as A and B. This is, the order doesn't matter here. It's commutative. So we can say that the probability of B given A is the same joint probability because they're equal, divided by the probability of A, the given thing. And what about independence? Independence statistically or in probability means that, well, here's the definition. It means that the joint probability is the same as the multiplying of the two probabilities together. Okay, if whatever event A is and whatever event B is, if we have A and B, the probability of that occurring equaling the probability of each event happening on its own, if those are equal, the two events are independent if and only if that's true. So if we can show that's true, they're independent. If we can show it's false, then we show they're not independent. That's what if and only if lets us do. If we're told they're independent, then we know this is true. If we're told they're not independent, we know this is false, because it's if and only if. Independent events have no effect on the probability of other events, of the other event that they're independent with. Therefore, for independent events, the probability of A given B is just the same as the probability of A happening. It doesn't matter that B happened. They're independent. Also, the probability of B given A is the probability of B. They're independent. Doesn't matter that A happened. So let's do some examples to make all this more concrete. A researcher is investigating a medication for preventing COVID-19. Starting with a group of 120 people, none of whom has COVID-19, so we test them, we know they don't have it. Medication is given to 80 of them and a placebo to the other 40. And the results are in the table below. Show why the medication helps, even though it appears that those who got COVID-19, 50% took the medication. So of the people that got COVID-19, here's the gets COVID-19. Half of them took the medicine and half didn't. So one person might say, well, look, half the people got it, and half of the people that got it, half of them took the medicine and half didn't, so their medicine's no good. But let's look at this table and show why that's not true, okay? So if we look at the table, we see that the probability of, so what we're kind of interested in is what's the probability that if we take the medicine, so given that we took the medicine, what's the probability that we got COVID-19? And then also, what's the probability if we didn't take the medicine, if we had the placebo, that we get COVID-19? That will tell us about how effective the medicine is. So if we get the medicine, what's the chance that we get COVID-19? Well, it's just 8 over 80. Because get is 8, total is 80. It should be 1/10 or 0.1 or 10%. If we take the placebo, what's the chance that we get COVID-19? 8 over 40 is our total, which is 0.2 or 20%. So by taking the placebo, our chances of getting, or our probability of getting COVID-19 were double. So the medicine is effective. It halved the probability of getting COVID-19. And of course, this is a big leap to make, and it depends on having a statistically valid random sample. There's no biases involved in order to make a conclusion. And there's lots of statistics that you can learn to help you make these conclusions, which we're not going to get into. It's a very basic overview of probability. A geneticist seeks to establish a link between a certain gene and a certain type of cancer. 250 mice are studied, and the results are below. For a random mouse from this group, so here's our events. A is picking a mouse with the gene. So the mouse has the gene as A. B is picking a mouse that doesn't have the gene. C is picking a mouse that gets cancer, which is convenient because cancer starts with a C. And D does not develop cancer. Okay? So we need to evaluate all the following probabilities given all that information. So let's start with A and C. What's the probability both A and C happen? Well, A and C happening is 10. There's 10 ways that can happen. And here we're looking at the entire total of all the events. There's 250 possible events, okay? So the chance that, that's the total mice, the chance that we, or the probability of both A and C, which is gene and cancer, would be 10 was our first number, over 250, which is 1/25 or 4%. B, the probability that cancer and gene, of course, is the exact same thing. Doesn't matter what order we do these in, 4%. C, probability of cancer and not gene. So going back to our table, so this was cancer and gene, cancer and not gene is 15 over 250, which would be 6%. D, the probability of A given C happened. Okay, so we can find this directly from the table. So the given C happened means we're just looking at these numbers. C has happened. Okay, so we want to know what's the probability of A given C happening. There's 10 ways A happens when C happens, and there's 25 possible outcomes. So 10 over 25. So when we have this table, we can just calculate this directly without having to use all those formulas we learned a minute ago. And that's 40%. So the probability of having the gene, given that you got cancer, is 40%. E, what's the probability of getting cancer given that you have the gene, the mouse? So now we're looking at a different thing. Let's erase this from my last problem. Now we're saying A happened. So we're looking at this column. A happened. What's the probability of getting C? 10/53. 10/53. It's 10 ways, 53 total. 18.9%. F, what's the probability of C given that you don't have the gene? So getting cancer without the gene. Okay, so now we're looking at, we don't have the gene. Given that we don't have the gene, what's the probability of cancer? 15 over 197. 7.61%. So is the probability of developing cancer independent from the probability of having the gene? So we can tell from E and F that they're not independent, because if they were independent, the probability of C given A and C given B, then we would have had, well, we would have had those be the same. So another way of looking at that is, what's the probability of C by itself? So the probability of C by itself would be 25 total ways C happens over 250, or 10%. Okay, so we can see that P of C given A does not equal P of C. Therefore, they are not independent. In fact, it looks like if you have the gene, you're much more likely to develop cancer than if you don't have the gene, based on E and F. We could go back now we can go back now to these definitions and prove independence from this definition. So what was the probability of the developing cancer independent from having the gene. Okay, so the probability of developing cancer is the probability of would be 25 ways to develop cancer over 250. We already said that. Probability of C is 10%. The probability of having the gene was the probability of A, which would be having the gene. So looking at, I'm sorry, that's not helpful. Probability of A would be the number of mice with the gene is 53. The total is 250. So 53 over 250. (21.2%). So what's the probability of A and C? We already have this here. It's 4%. Okay. So for the events to be independent, the probability of A and C has to be the probability of A times the probability of C. So the probability of A times the probability of C would be 10% back as a decimal, because when we multiply, we need to be sure we don't try to multiply percents directly, because then you would get per 10,000 as your answer, times 0.212. So 0.1 times 0.212 is 0.0212, which is not equal 0.04. So another way of proving they are not independent, or they're dependent. A new gene is studied. Is the probability of a mouse developing cancer independent of it having the second gene? So again, there's multiple ways to do this. We can find the probability of cancer with the gene, given the gene, and the probability of cancer given not the gene. Or we can look at the probability of having the gene and cancer, the probability of having the gene, the probability of cancer, and see if the probability of the gene times the probability of cancer, does this equal the probability of both the gene and cancer. So both the gene and cancer is 18 over 250. Just the gene would be 180 over 250. Probability of developing cancer would be 25 over 250. Okay, so 18 over 250 is 7.2%, the joint probability. The probability of A occurring is 180 over 250, 72%. And C is 10%. When we multiply 0.72 by 0.1, we get 0.072. So the answer is they are independent, because the joint probability equals the product of the individual probabilities. And we could also show that the probability of C given A is the same as the probability of C given B is the same as the probability of C. So let's look at that too. Probability of C given A, cancer given gene. So have the gene would be this column. So that would be 18 ways to develop cancer over 180, which is 10%. Probability of cancer given lacking the gene would be 7 over 70, which is 10%. And the probability of cancer would just be 25 over 250, or 10%. So you can see they're all the same, which also means they're independent. So there's two ways of answering this question. Suppose that the probability of event A is 0.5, B is 0.8, and A and B is 0.2. Are events A and B independent? So we just need to multiply Probability of A by probability of B. 0.5 times 0.8 is 0.4. Sorry, 0.4. So that does not equal 0.2. So the answer is no. They're not independent. B, compute A given B. Probability of A given B is the joint probability divided by the probability of B. So we can go back and just double check that from our lecture here. The probability of A given B is the joint divided by probability of B. Okay, so back to where we're working. A given B was 0.2, B is 0.8, so the answer would be 2/8 or 1/4, 25%. Part B, part C, probability of B given A would be the joint probability 0.2 over the probability of A, 0.5, 2/5 or 20%, 2/5, 40%. A new screening test for ovarian cancer detects 95% of ovarian cancers, really, is what it means. And has a false positive rate of 0.6%, or 6 per thousand. At any moment in time, assume 1 in 3,000 women actually has ovarian cancer. Supposing 2 million women take this test at once, essentially, construct a table of the results. What is the probability that a woman who tests positive has ovarian cancer? So imagine a woman goes to the doctor, gets this test, one of the 2 million. She gets a positive result. What we're trying to find is what is the probability that that woman actually has cancer. So if we wanted to guess from just the setup of the problem, we have this 95% rate. We would assume that means that she almost certainly has cancer. And the reason we're doing this example is we're going to find it's not the case. Okay, and that's why this is a really interesting problem. First of all, let's set up a table like we've seen in these other problems. That was very useful to have a table. So we're fortunate to be given a concrete number that we can go from of 2 million to help us put this table together. Maybe our table's a little bit small. We'll just trail off over here. It's no big deal. Okay, so on this end, let's do the testing. So here you we'll write this column as test positive, and this is your test was negative. Okay, here is you have cancer of the ovarian sort. That's what we're talking about in the context. And here you do not have cancer. And here this will be our totals. So our total will be 2 million because that's how many people take the test. Okay. So of the 2 million people, 1 in 3,000 actually has cancer. We're told that right up front. So let's find our calculator. Let's go ahead and start filling in what we know. So 2 million people. So 1 in 3,000 actually has it. So we'll multiply by 1 over 3,000 and get 666. And this is not a very good round number. I think maybe we should have made this 3 million. Let's do that instead. Because 3 million and 3,000, it won't really change our probability. It's just going to make our numbers nicer. So if we had 3 million and 1 in 3,000 halves it, then that'll leave us 1,000 people that have cancer. And 2,999,000 that don't have cancer of the 3 million people tested. Okay, so we're told that the 1,000 women who have cancer, when they take the test, 95% of the cancers will be found. So 1,000 times 95%, 0.95. 950 people will test positive that actually have cancer. and 50 will test negative. These are the so-called, I'm going to highlight this just so you know. These are the so-called false negatives, which there was no claim made directly here about false negatives, but a false negative means that you tested negative when you really had it. Okay. Now we had a false positive rate of 0.6%, meaning if I don't have cancer and I test positive, there's only a 0.6% chance of that happening for those 2,999,000 women. Times 0.6 gives us, 0.6%. So go back to 2,999,000, 0.006. 17,994 will test positive that do not have cancer because of this false positive rate. So here, these numbers in green that I'm highlighting is the false positives. People who are told they're positive that really don't have cancer. And that leaves left over for our negatives of, our true negatives would be 2,999,000 minus the false positives, 17,994, or 2,981,056. No, 6. 2,981,006. Okay, we can total this up, 2,981,056 and 18,944. So now I filled out this table. That was this first part of our problem. Construct a table. What is the probability that a woman who tests positive has ovarian cancer? Okay, so that we're trying to find is the probability of positive, no, the probability that a woman who tests positive. So given that you test positive, what's the probability you actually have ovarian cancer? Okay, so we can find that now that we have this table, because we can look at the positives. So the positives are here in this column. Now the positives, the ones that have cancer, is 950. And the total is 18,944. When we do the division, we'll find that we get 5.01%. In other words, if you test positive, there's only a 5% chance that you actually have cancer. Even though it looked like the test was really accurate, when you actually see these numbers, it comes out this way because of the fact that so few women actually have cancer. So there's millions of women that don't have cancer. A 0.6% false positive rate still ends up with a lot of people that get a false positive result. Okay, so if you were a woman and you were getting tested, I think you'd want to know this number, not these other numbers, because there's only a 1 in 20 chance that you actually have cancer, even though you got a positive result. Given the table below, for handedness and gender, find these probabilities. Okay? M here means male, and L means left-handed. So what's the probability that you're a male and left-handed? 6 over 100, or 6%. Female and left-handed. So here's the female left-handed, and female and left-handed would be 4%. What's the probability? And of course, this is the probability of these 100 people, right? Not the entire population. That's worth of noting. We didn't sample the whole world. This is not the universal probability. This is the probability given the people that were sampled. 100 people were sampled here. The probability of being left-handed, given that you're a male. Okay, so given male would be this row. Left-handed, there's 6 of 60, which would be 10%. What's the probability of being left-handed in female? Female rows, the second row, 4 out of 40, or 10%. Is left-handedness independent of gender? We could prove that by finding the probability of left-handedness, 10 out of 100, or 10%. And we see for sure that they are independent. Handedness and gender are independent, given this table.